All right, so Friday class is canceled or was canceled, and depending on when you are watching this video. And then I just want to go over what we talked on the Wednesday. That it was the first case of the internal flow heat transfer, where the surface temperature of the pipe is a constant. And then we construct a energy balance for a very thin slice of a flow or the unit volume, which is thin slice of the flow. And then we got this governing equation where the change of the energy on the left side, which is temperature change, equals to the amount of the heat transfer into the system. That's depending on the heat transfer coefficient H, and then the temperature difference, right? And then after we solve this differential equation, we get exponential decay of this delta temperature between the surface of the pipe and the flow. Basically, because of the heat change, because of the heat transfer from the surface to the flow temperature, the mean temperature of the fluid is increasing from purple to the blue to the green. So therefore, the delta temperature between the surface temperature to the flow mean temperature, in other words, the Ts minus Tm is becoming smaller and smaller. So therefore, the amount of the heat transfer gets slower and slower. So the temperature difference decays, eventually reaches zero, which means the fluid temperature reaches the surface temperature and there's no more heat exchange happening anymore. And today we will talk about case 2. And we still have a pipe. The flow will still coming from the left side at a low temperature, the cold flow, cold water coming into a pipe. And however, in this case, it's not the surface temperature of the pipe being a constant. Instead, the amount of the heat that has been transferred into the fluid flow will be a constant. So it will be a constant Q. And then when this type of thing will happen is when we typically, this is the case where we have a heater to heat up the fluid flow, and then the heater has its own fixed power, then the amount of the heat has to be transferred. And then in this case, we still can construct the energy balance for that thin slice. Here I have the purple, blue, green tells you the temperature is increasing from the left to right. And then the energy balance is still the same. That is the amount of the heat that has been transferred into the fluid flow or the system equals to the change of the internal energy or stored internal energy. And then I put a dot there, that will be the change rate. So that actually translates into the Q flux. That is the heat transfer flux times the surface area. The surface area of that thin slice, I just want to remind you, that thin slice is a shape like that, right? So this is a thin slice of a pipe, or it's a disk. And then the heat is actually transferred from the outer surface area of that disk. So therefore, the surface area is actually the perimeter of that circle times the length of that slice, which is delta x. So this is delta x, right? So the surface area is this area. That is the Q. And then the surface area will be the perimeter times x. That will equal to the change of the internal energy, that is the mass flow rate times the specific heat, and then times the delta temperature, delta mean temperature. Or you can use delta, or you can use the derivative. It really depends on how small you cut that thin slice, right? And then you make the delta x to infinitely small, and then this delta Tm will be infinitely small. So both will become D instead of delta. So the Q flux will be equal, I just rearrange this equation, M mass flow rate times specific heat divided by the parameter times dt over dx. That's the derivative of the mean temperature with respect to x. And then the dm, dtm, dx, that actually equal to q, p. And this is a constant. This is a constant because this is, the q is a constant. So therefore, everything becomes a constant. And then once this is constant, then you can integrate. As you can see, something's derivative equal to a constant, then Tm is a linear function. With respect to x. And then, okay, so this diagram was just showing you the surface area. So the surface area. This is the surface area for the heat transfer. So this surface area equals to pi d delta x, right? And then come back here, I can plot the mean temperature with respect to x, and it is a linear function with that. So at x equal to 0, this is T mean, T mean at inlet. And then it is a linear function like this. And then let me just use a different color. So this will be a linear function like this. And it's increasing until the total length of the pipe. And if you want to calculate the surface temperature, and we know the surface temperature, we know the Q would equals to the H times the surface temperature minus the mean temperature. By the way, I take the flux instead of the surface area. And then we know the left side is a constant. And that's why if the H is a constant, for most of time, H slightly changes depending on the property of the fluids, because we know in order to calculate the H, we sometimes have to look for the property of the fluids. And in the table, we sometimes can have a small change. And this one is roughly a constant, depending on how much the property has been changed in the internal flow. And then if these are two constants, and then this is also a constant. So therefore, the surface temperature will be roughly also a constant. So this will be the surface temperature, and this will be the mean temperature of the fluids. And the delta is a constant, or is about a constant. And then the slope of this linear relation, the slope slope, actually, you can see it is from this equation. It is Q flux times the parameter over the mass flow rate and the specific heat. And then that's it. Oh, well, one thing is if the Q is transferred from the surface to the fluid, so if this is greater than 0 from S to fluid, then Tm increase, right? So the slope is greater than 0. And then Q less than 0, that is from fluid to S, then the slope will be less than 0. So the mean temperature of the flow will be decreasing. And then on the other hand, the mean temperature will be increasing. All right, so that will be the second case. And we will use an example problem in the class to show this.